We start with the second talk of the afternoon session by Cristian Lenart on a combinatorial Chevalier formula for semi-infinite flag manifold and its applications.
Yes, thank you to the organizers for putting the conference together under difficult circumstances. Thanks everybody for coming. So I will talk about Chevalier formulas. And the talk is based on the joint paper with Satoshi Naito and Daisuke Sagaki, the first paper on the archive mentioned here. And I will also mention there are related results with Kouno, Takafumi Kouno, which are more recent, 21. And also I will refer to some older results of mine. So let me get started. So I will start with something very familiar with the Schur functions. So I should say that I'm also grateful to the organizers that they scheduled my talk right after Carola's, because it will make it very easy for me to refer to Schur functions, Schubert polynomials, Grothendieck polynomials, and so on. So starting with the Schur functions, to explain the simplest instance of a Chevalier formula, I will say that you take this basis of symmetric functions in infinitely many variables, Schur functions indexed by partition lambda. And if you multiply a general Schur function with a Schur function indexed by the partition 1 or 1, 0, 0, 0, which just corresponds in the Young diagram to a single box. And this Schur function is just the sum x1 plus x2 plus so on. And you want to expand the product in the basis of Schur functions, then you will get all the Schur functions indexed by partitions obtained from lambda by adding a single box in such a way that you still get a partition, and all the coefficients are 1. So that's the base case for me in terms of a Chevalier formula. But most importantly, the geometric interpretation is important in terms of Schubert calculus on flag manifolds. So it is well known that Schur polynomials represent Schubert classes, that is cohomology classes of Schubert varieties, in the cohomology of the Grassmannian of K-planes in C to the n, which is also a quotient of SLN by a certain parabolic subgroup. And as you can see, the cohomology is a certain quotient of the ring of symmetric functions in K variables. So in this sense, Schur polynomials lift Schubert classes to the polynomial ring. More generally, you consider the flag variety that was also considered here. So a point is just a chain of n vector spaces in C to the n. The dimension of Vi is I. This is also the quotient of SLN by the Borel subgroup of upper triangular matrices. And the cohomology here has, again, a basis of Schubert classes, which are indexed now by permutations W in Sn. And these classes are represented by the Schubert polynomials that Carola talked about. And here, the Chevalier formula is the simplest product that you can take. So Schubert polynomial indexed by W multiplied by Schubert polynomial indexed by simple reflection or an adjacent transposition of entries in position K and K plus 1, which can be written as x1 plus xk. And if you expand this product in the basis of Schubert polynomials, you get, with coefficient 1, all the Schubert polynomials indexed by permutations obtained from W by applying a transposition Tij on the right, where K is sandwiched between I and J. So the sum over all such I and J, also with the condition that the length upon applying the transposition increases by exactly 1. So that's the next Chevalier formula. So now we can generalize in several ways. So first we can replace cohomology with K theory. We can replace it also with torus equivariant versions of cohomology or K theory. Or we also have quantum versions. I will talk about them later. So we have quantum cohomology, quantum K theory, also T equivariant versions of these, where you introduce certain deformation parameters, which when you set to 0, you recover the ordinary cohomology and K-theory. Another way to generalize is to replace the variety, the flag variety I talked about, SLN mod B, or the Grassmannian SLN mod P, with the generalized flag varieties G mod B or partial flag varieties G mod P. And here G is a semisimple Lie group over the complex numbers, B a Borel subgroup, and P a parabolic subgroup. And also we have affine versions of these finite flag varieties. We have the affine flag manifold, and we also have something called the semi-infinite flag manifold corresponding to G. G is like above, which is like a non-standard way to define an affine version of the finite type flag manifold. Why should we consider these? Why it's interesting to look at these more general structures. So there are several reasons. First of all, quantum cohomology and quantum K-theory are related to physics. They are closely related to certain integrable multi-particle dynamical systems based on root systems called Toda lattices. Then there is a close relationship between quantum K-theory of the finite type flag variety and the K-theory of the semi-infinite flag manifold. This is a recent breakthrough of Sue Kato. And then there is also links to representation theory in the sense that the semi-infinite flag manifold has applications to the representation theory of affine D algebras. More specifically, we talk here about so-called level 0 extremal weight modules, which were studied by Kato, Naito, Sagaki, and also other people. So the plan of my talk is to introduce some background. Then I will introduce the related combinatorial model called the quantum Markov model, which is based on root system combinatorics. Then I will talk about Chevalier formula for the K-theory of the semi-infinite flag manifold, which is based on the quantum Markov model. Then I will talk about Chevalier formulas for quantum K-theory of the finite type flag manifolds G mod P or partial one G mod P. And then I will give applications, more explicit computations and results in type A. So for the K-theory of the type A flag manifold. So I will need some root system notation, but here you can always think about type A, as I will mention. So the torus, the Borel subgroup, and the semisimple Lie group G are as before. In type A, think of G as SLN and B is upper triangular matrices in SLN. Q is the root lattice, Q check the core root lattice, alpha I the simple roots. In type A, the roots are the same as the core roots, and there are differences of coordinate vectors epsilon I minus epsilon J in Rn. The simple roots are differences of consecutive coordinate vectors. P is the weight lattice, omega I the fundamental weights, P plus the dominant weights. So in type A, think of the weights as compositions. So just sequences lambda 1, lambda n of positive integers or non-negative integers. The dominant weights are partitions, so weakly decreasing such sequences. And the fundamental weights are just partition 1, 1, 1 I times. So think of it as a column in terms of the Young diagram representation. Then we have the group algebra of the weight lattice, which is the representation ring of the torus. Think of this as just spanned by the z-span of formal exponentials e to the lambda with the usual multiplication, exponential multiplication. And then we need the Weyl group, the finite Weyl group. Si are the simple reflections, so reflections in hyperplane orthogonal to the simple roots, and W0 the longest element. So in type A, W is the symmetric group. The simple reflections are adjacent transpositions, and the longest permutation is the well-known one. So let me mention some previous work. So first of all, how does the Chevalier formula look in K-theory? So think of K-theory or equivariant, torus equivariant K-theory of the generalized flag manifold G mod B as a module over the equivariant K-theory of a point, which is identified with this group algebra of the weight lattice. So this K-theory of G mod B has a basis of Schubert classes indexed again by elements of the Wahl group. And technically, these are the structure sheaves of Schubert varieties X of W. So they will be denoted like shown here. Then for a weight lambda, we have a certain line bundle on the flag variety, which we denote L lambda. It can be defined formally like shown here. And then the Chevalier formula expresses the product in equivariant K-theory of the class of this line bundle with the class of a Schubert variety indexed by W. And you expand this in the basis of Schubert classes. So you see here that you get the equivariant coefficients, e to the mu, the formal exponentials, and also some integers, which need to be specified, are specified by the multiplication, but we need to describe them. So with Alex Posnikov in 2003, we gave a combinatorial such formula in terms of the Alkov model. But now we need a more general model called the quantum Alkov model. And the foundation for this model is a structure called the quantum Bruja graph on the finite Wahl group. So you take the finite Wahl group, think of Sn in type A, denoted QBG of W. So this is a directed graph on the vertices being the elements of the Wahl group. And we have edges going from an element W to W multiplied on the right by the reflection corresponding to the root alpha. And we label this edge by alpha, by the root alpha, whenever we have one of two conditions. So either the length increases by 1 upon application of S alpha. These are just the covers of the usual Strom-Bruja order, or the length decreases by a lot, and a lot just means the maximum possible, which is this twice the height of the core root alpha minus 1. So the height is just obtained by expressing the core root in the basis of simple core roots and summing up the coefficients. So this is the Hasse diagram of the Bruja order for S3 with the labels on the edges. Alpha ij is the root epsilon I minus epsilon j. And then we also have to add these down edges, these quantum edges. For instance, we have a down edge from the longest element 3 to 1 to the identity, because we can switch 1 and 3, and there is a large decrease in length from length 3 to length 0. So then the quantum Alkov model I introduced with my PhD student, Arthur Lubovsky in 2011. So this is based, so first of all, it's associated to a weight lambda. Think of it as a composition in type A. And with any such weight, we can associate a sequence of roots called the lambda chain. So beta 1, beta m are roots. And this sequence is determined by a reduced decomposition of the affine Wahl group element corresponding to the translation of the fundamental alcove by negative lambda. Basically, it gives you a shorter sequence of adjacent alcoves joining the fundamental one to the translated one by negative lambda. So here's an example. So in type A2, if you take the weight 310, so 3 epsilon 1 plus epsilon 2, you see here the projection of the roots from R3 to R2. In blue, you see the coordinate vectors, epsilon 1, 2, 3. In red, you see the positive roots, epsilon 1 minus 2, 2 minus 3, 1 minus 3. And then you see the hyperplanes orthogonal to these roots, and also translates of them. And the orthogonal complement of these collections of hyperplanes are the triangles, which are the alcoves. And then the fundamental alcove is the shaded ones centered at the origin. And at the bottom of the diagram, you see the weight negative lambda. So minus 3 epsilon 1 minus epsilon 2. And then you want to join the fundamental alcove to the shaded one at the bottom, the translated one by negative lambda. And you keep track of all the hyperplanes that are crossed. Namely, you look at the roots that are orthogonal to these hyperplanes. And that's the lambda chain. So you see the first hyperplane that's crossed at the top is orthogonal to the root 1, 2. And then you have 5 more hyperplanes that are crossed. And you get the lambda chain shown at the top, 1, 2, 1, 3, 2, 3, 1, 3, 1, 2, 1, 3. So now, given such a lambda chain, Ri is the reflection corresponding to the ith root, and Ri hat is the affine reflection because these are affine hyperplanes corresponding to the ith crossed hyperplane. And the objects of the model are subsets of the indices 1 through m, which you think of as positions in this chain of roots. And given such a subset of positions, and also given a Weyl group element, you can construct a sequence of Weyl group elements starting from the given W and multiplying on the right by the reflections corresponding to the roots in positions J1, Js, one by one. And then you end with some Weyl group element, which we called end of W and A. So A is the sequence of positions and W is the starting element. And then we introduce W admissible subsets. We don't want all the 2 to the m subsets. We only want those ones for which this sequence of Weyl group elements is a path in the quantum Bruhat graph. And then we have some statistics associated to a pair WA. Well, we first of all have the end of WA, the ending Weyl group element, but we also have the weight, which is obtained by applying these affine reflections Rj I hat to negative lambda, and then W at the end, and also changing the sign. Then we can keep track of this, of the places where in the associated path in the quantum Bruhat graph, we have these down steps, these quantum steps. And we keep track of those positions, Ji, where we have these down steps. So this is a subset of A minus. And then another statistic down of WA is obtained by summing the appropriate positive roots denoted by beta bars. The absolute value of beta is just the corresponding positive root in case the root is negative, actually the core root. We just sum those core roots made positive in the places where we have down steps. So now this model is known to be independent from the associated lambda chain. So in other words, if there are 2 lambda chains, gamma and gamma prime, then there is a surjection between the Alkov model for gamma and between the admissible subsets for gamma and gamma prime, which preserves the relevant statistics. So this is a result with Kono and Naito. And this is based on certain moves which generalize root system, which are root system analogs of Jeu de Taquin slides for semi-standard Young doublet. So now we have, first of all, a Chevalier formula for semi-infinite flag manifolds. As I'm a little bit short on time, I will not give many details on this. We just very briefly, we use formulas given for dominant weights, Chevalier formulas for dominant weights and anti-dominant weights of Naito, Sagaki, Kato, Naito, Sagaki, and Orr, which are expressed in terms of some continuous model called quantum Lakshmi by Seshadri paths, and we translate them to the quantum Alkov model, and then we put them together, we combine them to get a formula which is a multiplication formula for a line bundle corresponding to an arbitrary weight. But most importantly, I want to get to quantum K theory. So here we have deformation parameters Q1, QR in the base ring, in addition to the group algebra of the weight lattice. So the quantum K theory is a tensor product as a vector space of usual K theory with this ring of deformation parameters and equivariant parameters. And here we have a basis of Schubert classes. And to any element of the Poirot lattice, we can associate a monomial in the deformation parameters. So then I just want to show you the Chevalier formula, which was conjectured by myself and Alex Postnikov in 2003. Here we have to take a chain of roots corresponding to the negative kth fundamental weight. And then we have a cancellation-free formula, which expresses the product in equivariant quantum K theory of an arbitrary Schubert class with a Schubert class indexed by a simple reflection. And you see here, in this expansion, you see the statistics down, the weight, and the end. So we have the equivariant parameters e to some power, where the weight is relevant. And then we have the quantum parameters q raised to the power down of wn. So this follows from the formula that we derived before in the semi-infinite flag manifold, because there is an isomorphism due to Kato between quantum K theory and the K theory of the semi-infinite flag manifold. We also have some results for partial flag manifolds that are derived from the Chevalier formula that I've shown for the full flag manifold. But here we get lots of cancellations if we just apply this surjection of Kato from G mod B to G mod P, and we have to perform all these cancellations via sign reversing evolution to derive a cancellation-free form. But most importantly, I want to end by talking about Grothendieck polynomials that Carol also mentioned. So these represent Schubert classes in K theory of the type A flag variety. And then we can quantize these. So we define some analogs of the elementary symmetric polynomials in the quantum parameters. And then we have a quantization map, which takes this basis of standard elementary monomials, so product of elementary symmetric polynomials, and associates the same product, but with the quantized versions. And if you apply this quantization map to the Grothendieck polynomial, you get what's called the quantum Grothendieck polynomial. So this we defined with Maeno in 2006. And Fomin, Gelfand, Postnikov did the same thing for Schubert polynomials before. They defined quantum Schubert polynomials. So with Maeno, we showed that the quantum Grothendieck polynomials satisfy the version of exactly the version of the above Chevalier formula that we proved before. We proved in arbitrary type, but now we just need it, and also equivariant K theory, but now we just get it for quantum K theory of the type A flag variety. And as a corollary, we proved this conjecture, this old conjecture with Maeno, that the quantum Grothendieck polynomials represent Schubert classes in the quantum K theory of the type A flag variety. We can finally prove this conjecture. Which means that we can use the quantum Grothendieck polynomials to expand any product of Schubert classes in the basis of Schubert classes in the quantum K theory of the type A flag variety. So we can solve this very big generalization of the Littlewood-Richardson problem algorithmically, because not even for the cohomology of the type A flag variety do we have yet a nice general rule. But at least algorithmically we can do this. And finally, also as a consequence of our formula, we can show that if we take the expansion in quantum K theory of the type A flag variety of the product of an arbitrary Schubert class with one index by a simple reflection, so we take such a Chevalier product, all the coefficients in the expansion in the basis of Schubert classes are plus or minus 1, and they are explicitly determined. So I'll end here.
All right, thank you very much for the talk.
Thank you.
Are there any questions? And don't be shy. Unmute yourself, ask the question.
Just the last formula, so if you have all plus ones, it's usually it's related to multiplicity-free modules. So is there here multiplicity freeness or something, but you have minus ones, this what bad.
Right, the minus one is just natural because we have this alternating property for growth-indeed polynomials, and the Littlewood-Richardson rule is alternating. Everything is alternating. So, the minus ones are really controlled, well controlled, where they appear. The minuses.
So you have multiplicity freeness here.
In type A, yes, we do have. I don't know about any modules, so maybe it's related to these level 0 extremal weight modules, because that's the representation theory behind everything I said today.
Bijections, by the way, are not immediately obvious terminology, but I could look them up. So
Right. So they were introduced by Ilse Fischer and Matthias Kohn-van Linka in their bijective proof of the alternating sign matrix conjecture. Right. So yeah, they introduced this definition to give the bijective proof. So yeah, they are bijections between sets where elements come with signs.
Okay, any other questions? This is not the case, then thanks again for the great talk.